on working memory as well as on visual memory. And so far we've talked almost exclusively about primary sensory cortex, for example, primary somatosensory cortex and primary visual cortex back here. But there is a higher order cortex known as association cortex. And with association cortices, these areas specialize in tying together different sensory modalities, processing the information and passing that information on to motor areas further in front of the brain, in the front regions of the brain. And these association areas take up the vast majority of human neocortex. And you can see the association areas here in deep purple. You've got posterior association areas as well as association areas in the limbic system, the temporal lobe, and of course the anterior association areas in the frontal lobes. You've got your primary visual cortex back here, your primary somatosensory cortex, and your primary motor cortex here in front of the central sulcus. So a large part of our neocortex is primarily involved in integrating different modalities of information. And there's, again, a logic to the whole system such that you've got primary sensory cortices that receive information about particular aspects of the environment. They then pass the information on to what's known as unimodal association areas that integrate multiple types of information from just one sensory modality. For example, if it's touch, the sense of touch, the unimodal association area would integrate information on texture of an object, shape of an object, and so on. If it's vision, the unimodal association area for vision would integrate multiple aspects of visual information. For example, color, shape, position of the object in space, and so on. So once the unimodal areas process the information, they then pass it on to multimodal sensory association areas. So there's a clear hierarchy beginning with primary cortex at the bottom, unimodal above it, multimodal sensory association areas even higher, positioned even higher. And the multimodal areas, as you can imagine, integrate multiple sensory modalities. For example, information regarding sound and sight. And that's the peak, the top position of the sensory areas, the multimodal association areas. And from there, the information then gets passed to the motor centers, in particular to multimodal motor association area, located in the frontal lobe. Okay? So information progressively moves from the posterior regions, sensory regions, forward to the frontal areas, where there is multimodal motor association function. And from the multimodal motor association areas here, the information then gets passed progressively backwards again, first to premotor cortex, and then finally from premotor cortex to primary motor cortex. And it's the primary motor cortex that is responsible for initiating voluntary movements, such as reaching out for an object. So you have this systematic hierarchy moving from primary sensory areas in the posterior regions forward to unimodal, multimodal sensory, multimodal motor association areas, and finally primary motor cortex through premotor cortex. And the function of the premotor cortex and the motor association areas, multimodal, is to plan, select, sensory information processed back here, which moves progressively forward to generate motor command signals in the frontal cortex and premotor cortex. Now, what's interesting, don't write this down because I'm not going to test you on it. You encounter it if you take Physiology 372 systems neuroscience. There are neurons in premotor cortex in monkeys as well as in humans that are called mirror neurons. Some of you might have heard about it. So these neurons fire when you perform an action, such as reaching, but also when you observe someone else performing the same action, even though you're not carrying out the action. That's why they're called mirror neurons. We don't really know the functions of the neurons. Ideas have been put forward that these neurons are essential for learning motor tasks. For example, a human infant might observe a parent doing certain things and will copy that imitation process. There are some who claim, without much evidence, it's still a hypothesis, that mirror neurons are dysfunctional or messed up in children with autism. Although there isn't really any convincing proof for it, but it is quite a widespread theory. It's not the only thing that goes wrong in the brain of autistic children, but it's been proposed that mirror neurons might be not functioning properly in children with autism. So, getting back to the cortex, let's look now at prefrontal cortex. And the prefrontal cortex is largest in humans compared to other mammalian species. And it's critical for what's known as the temporal organization of behavior, the ability to organize behaviors in a logical, sequential fashion. And with experimental lesions in monkeys, what you find is that the prefrontal area, if it's lesioned, the monkey has a hard time initiating and executing behaviors that have a purpose, purposeful behaviors. Basic movements, eye movements, etc., are perfectly normal. The animal just cannot execute complex, purposeful movements, sequences of movements. IQ in humans or general memory function are basically intact with frontal injury, if the injury is not too extensive. To the extent that what you find is that working memory is impaired. So, in humans, prefrontal cortex is really important for linking, remembering links between sensory cues in the environment and particular motor actions. That's what we'll see later on with some of these experiments with trained monkeys. So the ability to link certain sensory cues in the environment with future motor actions requires circuits within the prefrontal cortex. It's also important for short-term memory, otherwise known as working memory. So an example of working memory, because it's short-term, short-lasting, is if you were on the phone, cell phone with a friend, and your friend asked you to copy down a particular number, and you didn't have a paper and pen with you, and therefore you need to memorize it just long enough so that when you hang up, you can write it down on a piece of paper. That's short-term working memory. Once you break down the number, of course, it's evaporated. It's no longer in your memory today because you no longer need to use it. So it's called working memory because the information there is there only long enough so that you could use it for a particular purpose. Once you carry out that action without use of information held in short-term memory, you no longer need that piece of information, and therefore it's erased, it's forgotten. So how do we explore the functions of the prefrontal cortex in the context of working memory? To really explore its mechanisms, you need to do electro recordings from single units, single cells. And to do that, you need to use an experimental animal that is as close to humans as possible. So here we introduce our friend the monkey. Usually it's a macaque monkey, not a chimpanzee, but a macaque monkey. And there are variations of a task known as a delayed action task. There's a delayed response, alternation, and matching to sample task. I'm going to focus mostly on the matching to sample task, or in some cases it may be called the non-matching to sample task. And with the matching to sample task, DMS, the animal is first presented with an object, usually a colored object, in this case red. The screen drops down to block its view of the object for a fixed amount of time. This is called the delay period. So the animal sees a blank screen, and then the screen is then raised, and the animal is presented with a choice during the choice period. And in the matching of sample test, the animal needs to reach out and press the original cue object, in this case red, not the green object. With the non-matching the sample task, the animal has to touch the novel object that it had not previously seen during the cue. Okay. And the period during which the screen is down, the so-called delay period, is usually a couple of seconds. What's the motivation for performance? If the animal makes the correct choice, he gets a truth reward, a truth reward. So during this entire process, you can record from single neurons within the prefrontal lobes of these monkeys. They're wide awake with a chronically implanted electrode. They're free to move their heads and their arms. They're basically seated in a chair. If you plot the histogram of the electrical firing rate, spikes, it leaves a number of action potentials over time. What you find is that there's a stable baseline firing rate during the cue or sample presentation. And then when the screen drops down to block the animal's sight during the delay phase, there's a significant increase in the activity of some of these cells. That persists for the entire period of delay, the delay period. And then when the screen is lifted up and the animal is faced with a choice, and he makes the choice, the firing rate drops down to control pre-training levels. So what's interesting is that this increase in activity during the delay phase seems to be reproducible, occurs quite frequently in several prefrontal cells. Here's a picture of a monkey presented during the cue. In this case, it's a non-matching to sample task. It's presented with half a Canadian football. It's Canadian football because of the stripe. If it was an American football, it wouldn't have the stripe. It would be lost ball. Maybe this was better than Canadian one. So anyway, there's a monkey. I don't know why the images are so pitch dark up here. They look great on my screen. Something fishy. So that's during the sample phase, and this is during the choice phase, where the animal is presented with a novel object as well as the original object, and has to reach out and touch the non-matched sample, the new object, in order for it to get the reward. here again is our action potential of 4 cells. You see these vertical lines, the Q is presented here, the sample output, and then there's a fixed period, delayed period, during which the animal has to hold in its memory the nature of the Q object. And then here is, at the arrow, is the choice phase, where the animal has to choose the object. So what you find is that there is a consistent and significant increase in firing of these prefrontal cells during the delay phase. But in many cases, not in all cases, but in many cases, when the animal is choosing the object, reaches out and touches the object, in other words, carried out the motor action, these cells tend to reduce their fire rate in some cases. So it's almost as if the cells are storing the memory of the cue just long enough so that the animal can perform its learned task, reaching out. And once the animal performs that task, the firing rate falls back down to basal level. You'll notice that in the other cases, in these 2 other cells, the cells keep firing. So there is some variation in the pattern of the response. In general, it was believed that this increased firing during the delayed period in the prefrontal cell represents a temporary working memory of the particular location or nature of that original cue. Now, instead of reaching out, training a monkey to reach out and touch the appropriate object, which takes months. I mean, there's a common myth that monkeys are really smart animals. Well, you talk to a neurophysiologist who works on monkeys, that's not me. There are a couple at Queen's University, more in San Francisco, they'll tell you. They wish they had worked on rats. It takes months to teach a macaque, a young macaque monkey, a simple movement like reaching out on cue to a particular object. A human infant, 6 months old, can master a task like this in minutes. And yet, a 6-month-old macaque monkey takes up to 4 to 6 months to be trained on this task. The problem seems to be that macaque monkeys are quite restless. They're consistently, continually searching for novelty. So to have them sit still, they actually strap them into a chair, a barbed chair, you actually train them to sit still and pay attention to a cue, and then to reach out on cue during the choice phase. That's a very task while recording all along. They don't seem to mind the recording because it's perfectly right. So the myth is out there. It's true. Monkeys are not as smart as humans. Obviously not. Even though they've got less than, I think 1 to 2% of their genetic material. Only 1 and 2. There's only a 1 to 2% difference between our genome and the monkey genome. And yet there's a world of difference in learning capabilities and health. So apart from reaching, training a monkey to reach, you can also train a monkey to make an eye movement. And you can track its eye movements while recording the activity of prefrontal neurons. This is what the late Patricia Goldman-McKeith was able to do many, many years ago. She was a neuroscientist at Yale University, one of the most prominent in the 20th century. And she was able to train monkeys to perform a quick eye movement on cue. So the monkey will be viewing a TV screen, and it will be trained to fixate on a central point. Okay, there's a fixation. Then a target object would appear momentarily at any one of several positions. In this case, it's at the 1 o'clock position. Then the target would quickly disappear. That would be your delay phase. All along, the monkey And then during the choice phase, after the delay, there would be a cue, sometimes an auditory cue, and then the animal would be trained to quickly move its eyes and look at the point in space where the object had been previously shown. Okay? So in this case, a correct response would mean the monkey would be making a quick eye movement, looking at the 1 o'clock position, even though the object is no longer there. So instead of an arm movement, there you have an eye movement. So what her lab has done was to explore the firing rates of neurons in the prefrontal area of these monkeys as a function of the position of the original cue. So here are the raw firing recording. See the cue, the delayed phase, and then the response of the short phase. And here's the actual TV screen, the fixation point. So the monkey would be staring at the fixation point. And then the visual cue would appear in any one of these several positions. Okay? So these are recordings from a single cell. And you'll notice that this cell has significantly increased activity during the delay for when the cue was presented here, in this quadrant, here at 12 o'clock, or here at 9 o'clock, but much less firing elsewhere. So she called these cells, of course, memory cells, but she also introduced the term memory map. Okay? Much like a spatial map, which we'll talk about Friday's lecture, hippocampal neurons. But also she introduced the term memory field, which is analogous to the receptive field we talked about in the somatosensory cortex. A memory field is simply the area or specific locations where these cells would selectively fire during the memory phase, during this delay phase. Okay? So it's a memory field. It's not strictly a sensory receptive field because no neurons, no receptors are being touched. But it is a memory field. And she had proposed that memory fields and the memory maps associated with these fields may be the cellular correlates of working memory. So the central idea in the memory research field is that there has to be a cellular basis, a physical basis for memory. When we store and remember something, there has to be physical changes in our brain. Synapses might be strengthened or sometimes weakened. Neurochemicals might be upregulated or downregulated. Receptors might be inserted or taken out of the memory. There has to be a physical change, a trace, a memory change. And those are how we make up the cellular correlates, and their manifestation out here in space when you do these type of experiments is a memory field or a memory map. So this particular cell has a memory map out about, or a memory field at about 10 o'clock and 12 o'clock. So even if you take a look at the prefrontal cortex of the monkey, you find that within the prefrontal cortex there are subregions. There's a ventral region and there's a dorsal region. And neurons within these regions can probably encode different aspects of an object. For example, neurons that are in the ventral region, okay, of the prefrontal cortex tend to encode information on what an object is. Its identity, whether this is a tennis ball or a football. Neurons that are more superior or dorsal to the principal sulcus within the prefrontal cortex tend to encode information on the location of an object, where an object is. And there are, of course, many other neurons that seem to do both. So there's a mixture. And we now know through more recent research that the firing that you saw during the delayed phase in the prefrontal cortex is not purely a memory signal per se. What it is a preparation signal for an impending motor action. I know that sounds a paradoxical term, but it's captive memory of the future. You certainly have memory of the past, but memory of the future. And in my next lecture, my last lecture on Friday, when we talked exclusively about hippocampal neurons, just a footnote, I'll say it now because it's not on the slides. Turns out that the hippocampus, as you know, is critical for making new memories of people, places, and things. We now know that on top of this, human patients with injury to the hippocampus also cannot imagine the future. That's cool. So if they were given a fixed set of facts and asked to use those facts to construct a future scenario, they have a hard time doing that, even though they have the facts themselves. So maybe their hippocampal neurons may also be involved in memory of the future in the sense of constructing future events. Yeah? So the question is, does the increase in firing in the delay phase occur only because the monkey has been previously trained to make a select movement? Right? In most cases, that's true. Absolutely. You don't see the increase in a poorly trained monkey that has a 50-50 probability of making the correct choice. So choice accuracy, correctness correlates with firing. So that's prefrontal cortex. Now I want to move on to what I consider to be infinitely, exquisitely more interesting. That's visual memory. So if you look at cells in primary visual cortex, just to review for you, some of these cells are quite simplistic. They'll fire in response to a simple bar of light that's oriented in a particular manner. This was the work of people in Beetle back in the 50s and 60s. So shown here is one such cell. Here's the receptive field of the cell. So they've got a cat seated in front of a screen like this, and then they have a narrow bar of light, and they can orient the bar of light in various ways and move it in particular directions. So for this one particular cell, the cell has a preferred orientation of this, but not of these other orientations. So its receptive field properties are quite specific. But outside of V1, you have visual areas with more complex requirements, more complex receptive fields. And these areas are called collectively extrastriate cortex, outside of the striate cortex, which is V1. So in monkeys, particularly rhesus monkey, we have as many as 25 distinct subregions of extrastriate cortex devoted to visual processing. And humans and monkeys, and to a certain extent cats, are very visual animals, highly visual. A lot of cortical real estate for visual processing. And the term visual perception, I think, best expresses this complexity of processing. We are nowhere near understanding how our brains reconstruct a complex visual scene from memory, or even from real-time experience, not even from memory. And just to give you an example, this was called V1, the primary visual area, which is the lowest in motion. So many years ago, there was an elderly lady, a clinical case study, who happened to show up in the clinic and complained that for her, everyday life was like watching a slow motion movie, stop frame. So one moment, she would see her grandson here, she'd blink, and the next moment, the grandson would be over here. She missed entirely the smooth motion from left to right. And so clinical neurologists performed functional MRI on her brain, couldn't figure out what the heck was wrong. Because her retinal responses were perfectly normal. She had 20/20 vision. Her visual acuity was perfectly normal. She could see color perfectly fine. She could name an object. What is this object? They couldn't figure out where in the brain her visual deficit was until they did functional MRI. And it turned out that she had suffered a circumscribed stroke, tiny stroke that took out a small chunk of tissue while within the temporal lobe. And that area happened to be V5. And it's probably responsible for her inability to discriminate smooth motion. So you would have poured, so she had terrible difficulty pouring a glass of water, filling a glass of water from a pitcher of water, because she was unable to perceive the smooth movement, the smooth flow of water. And as you know, movements like that rely on sensory feedback, visual feedback. So in order to accurately pour a glass of water, we need that constant motion feedback from the water flowing down the pitcher in order to control the movement and avoid spilling the water outside the glass. She couldn't do that. And she had a terrible time, miserable time, as you can imagine, watching a hockey game. Live. So that's just an example of extrastriate cortex. You've got cells that enable us to perceive smooth motion. In V4, you've got cells that enable us to discriminate very subtle shades of color. V4 is a big time center for color processing. Okay. Now, years ago, neuroscientists in monkeys, using monkeys, were able to elucidate two major visual pathways. One that's, well, both start out in V1 and then progress anteriorly. There's a dorsal pathway and a ventral pathway that terminates in the temporal lobe, particularly the inferior temporal lobe, which is this strip right here. This is superior temporal lobe. That's inferior temporal lobe. So there's a dorsal and a ventral pathway. V4 is about here, deep within the cortex. V2 is here, and V5 is way in here, tucked in. It's a tiny structure. So, if you injured your dorsal screen, which terminates in the posterior parietal cortex behind the primary sensory cortex, the major sensory impairment would be a disruption of performance on tasks that link spatial location to action. So you wouldn't be able to recognize the location of an object and use that information to carry out visual spatial tasks. With the ventral stream, more interestingly, in my opinion, a lesion or injury to that pathway impairs the ability to recognize familiar objects. Now note, in all of these cases, visual acuity is perfectly normal, 20/20 vision. Color perception is perfectly normal. So these are very specific impairments. In the case of the ventral pathway, there's an impairment of the ability to recognize objects. In other words, it's the skill we use in order to discriminate between different objects. So So if you have a container full of pens and pencils, you want to reach for a particular color pencil, not pen, you're going to use your ventral pathway a lot in order to do that. And indeed, within the inferior temporal cortex shown here, if you record it from some cells, not all cells, there are some cells that will fire selectively when you see a particular face at a particular angle, and not another face. And these cells were originally called GMCs, or grandmother cells, because the scientists propose that these are the cells that are responsible for us being able to recognize our grandmother in the current future. Now, it's overly simplistic to think that there's one cell in our brain for each individual face. That's wrong, as we'll see later on in the presentation. More likely, there are circuits or columns of cells that fire together in order to mediate recognition, facial recognition. So in this straightforward but classic experiment, a monkey is facing a projection screen, and on the screen is projected another monkey's face at various angles. And all the while, they are recording from a single cell in the inferior temporal cortex, which is the termination point of the ventral pathway. What you find is that this particular cell has a preference for this image or for this image, and with much less firing for the other image. So these cells in general respond not so well. They don't fire briskly to simple shaped objects. They seem to be specialized for more complex three-dimensional objects, such as faces. There are other cells that fire with a very subtle distinction. So in this case, for this one particular cell, cell 1, it fires preferentially when this object is presented on the screen, but not when this object, these two objects are presented. And the only difference, of course, is very subtle. And yet the firing rate changes dramatically. In cell 2, the same thing. Even though this object resembles this object, the only difference being that there's a separation of the two bars. There's a dramatic difference in firing rate. So the horizontal line here shows the exact time when they present the image. And just to push it even further, for this one particular cell, it fires most briskly when this image or this image is presented, but not when this image is presented. And again, the main difference is this protrusion. Well, what's remarkable about this cell is that you see these two objects. The only difference is that this has a rounded edge, and this has a square, sharp edge. And yet, look at the difference in firing rates. So some of these cells in the inferior temporal lobe are highly tuned to very subtle changes in the visual stimulus. You can't get more subtle than that. So you can actually design a computer program that takes an image like this, a tiger's head, and create fundamental building blocks of the tiger head, and then breaks down the building blocks to see just how far the cell will fire. So in this case, the one cell kept firing even though the image was broken down to this or this. But the cell stopped firing when the image was broken down into a single square or two rectangles. So there is a limit to the specificity. you break down an object too much, the cell ceases firing. Or more correctly, the cell's receptive field properties fail to be satisfied. And again, scientists have found that it's populations of neurons that fire that can account for our perception of single objects, not singular. There just aren't that enough neurons in our brains to fully account for the seemingly infinite number of objects, faces, that we can recognize. So how are these populations of neurons organized? Not surprisingly, they're organized in vertical columns. And in very clever experiments using brain imaging, metabolic imaging in monkeys, and likely anesthetized monkeys, what they found was that clusters of neurons became more active, took up more of the marker on particular light orientations were presented to the receptor fields. So in this case, this presentation of this or this increased the firing of this cluster of neurons. So you're looking down on the surface of the inferior temporal lobe. This is a surface image using a special microscope. So you see this dark region, that's the active area of cortex. And you can see here we're looking at about 5